At this point, we now have big step evaluation that we specified in a previous sort of sense, previous chapters, at least for IMP and so on. And the small step reduction for this simple language. So a reasonable question to ask actually is, if you've got these two notions of evaluation, are they consistent with each other? And it, again, this is something that a programming language theorist would actually care about, because there's no point in having two different notions of evaluation that if you're trying to prove properties about things, you'd like to know that you're not proving those properties about different notions. So in this particular case, we defined earlier in the chapter, we defined this notion for this simple constant plus language. We defined this notion of big step evaluation, so t evaluates to the number n. So what we want to show here is that if that's the case, then t multi-steps to that constant n. Again, for all t's, in other words, every possible term that we could have. And this sort of sketch of the proof essentially shows you what's likely to happen is that if you start out with a constant, everything's very easy. But if you start out with a plus, you sort of have to crank the handle on single steps of the first part till it becomes a constant, and then crank the handle on the second part until it becomes a constant, and then you get this constant. Okay, so that's the typical sort of evaluation for single stepping. But if you think about the way the definition of this evaluation was defined, was that you basically evaluate the two children independently to get constants, and then you add them together to get the final answer. So it should be clear that once you have enough single steps in a row, you get to the same point. So we're not going to prove it, but you can try it if you want, but that's definitely possible to do. This is the other direction of that evaluation, which is basically using this lemma basically here that says if you've got if t prime evaluates to n and t single steps to t prime, then t also evaluates to n. So this is sort of making a single step relationship between the two kinds of evaluations. So if we essentially taking a big step relation and sort of extending it backwards one single step to get to t. And you can use that to prove this theorem, which says that if t prime is a normal form of t, in other words, you can get to it via some sequence of single step reduction steps, and there are no more. It's the last one. It's normal form, so you can't make any more steps from there. Then there has to be an n such that this thing that we've got is a constant, and that's pretty easy because we showed before that all the normal forms of this step relation were values, which are constants in this case, and it has to be the case that t evaluates to n to the same n as the term. So that's not trivial to prove, but it's not going to use any techniques that we haven't seen so far. Okay, so for the last part of this, I just want to do the well, not do, but sort of consider what would have to happen for the IMP language for this small step sort of idea. So I'll scroll down to where that is. Again, there's a bunch of different exercises for this material. Now the reason they didn't do imp for the whole chapter is it just gets quite involved, obviously, because there's a lot of constructs in the imp language compared to that simple language, and just the ideas get sort of bogged down in the complexity of it all. So here they're just going to sketch out what happens. We're not particularly interested in the detail here either, but just to see how it looks basically. So remember, in the imp language we have arithmetic expressions, Boolean expressions, and commands. So we need a notion of value and stepping for each one of those. So here's the definition of an arithmetic value is just a number. And we have this relation here which relates to expressions, states, and expressions. And this A is denoting that this is the single step for arithmetic expressions. And it's defined some length here. And what you'll see is if you look at this closely, you'll see that it basically mirrors the definition of the C and P language that we did before. So for example, these three rules are almost the same as the plus rules that we had in that simpler language. We have one form that has two constants in it, one form that has to step the first part, and another form that has to step the second part if the first part is a value. So these three rules are analogous to the rules that we've seen before. There's three similar ones for minus and three other ones for mult, so they're all following the same pattern basically. And the other one is the rule for identifiers. So if you have an identifier and you want to single step it, you step it to a number which is the, you step it to a number which is the value that's in the state for that identifier. So this is obviously more complicated, but the concepts are basically the same concepts as we've seen. We can do an analogous thing for Boolean expressions, which is even longer. Right, so this is basically following the same sort of pattern as before, but there's a bit more complexity because of the way Boolean expressions work. But you can see, for example, in the equality case, there are three rules just like there are for the plus and the mult and so on. And then the C step ones are a little bit more involved as well. So some of them are pretty basic. So for example, if you have an assignment and you can step the expression, then you just step the assignment to another assignment with the same expression, the stepped expression in it. But if the assignment is a number, which this number can't step, then we say that the assignment disappears to become skip, but the state changes to be the updated state. Now this update to skip is a bit weird, because why are we turning into skip? We just want to evaluate it. But if you think about evaluating commands in a small step fashion, to actually evaluate this assignment, we have to make it disappear, otherwise it's going to get evaluated again, for example. So the skip's the way to do that because it has no effect. And so when it's combined in, say, a sequence or something, the skips all disappear, basically. So for example, in the sequencing one, if we have this sequence C1, C2, if we can step C1, then we get another sequence where the C1 is stepped. But eventually C1 will turn into skip, in which case we then pick up with stepping to C2. So the first part of the sequence has disappeared. And the same strategy works for most of these. The while one is sort of interesting because the while steps a while to an if that contains the same while and a skip. Right? So we're just doing loop unrolling one step here by pulling the C1 out, one copy of the C1 out the front and doing it, and then going and doing the while again. But we only do that if the Boolean condition is true, otherwise we do skip, which terminates the iteration. Okay, now they haven't done the proofs for determinism and comparing this to the big step relation and so on and so forth. If you've got some time on your hands, you could have a go at that. It should be possible, but it will take a bit of work to get to that point. All right, so that's the end of this this material. So we've seen a way of formalizing the reduction, i.e. the evaluation of a language in small steps instead of big ones, where we get to capture every bit of the evaluation that goes along to get to a final answer, which we've introduced terms like normal forms and strong progress and normalizing relations to do with, do these always terminate, and do we always make progress at each step, and so on and so forth. Now obviously in this chapter we've only done a very simple language, so we're not applying this to full-on languages, but the small step ideas do translate into bigger languages. But because of the extra detail involved, mostly people will use big step semantics if they can, because it's easier to use. And that's why proofs of equivalence are important, because if you plan to work in big step semantics but use that to work out some things about where small step semantic ends up, you need to have some equivalence between those. Okay, so I'll stop there and pick up next week with some lambda calculus.